All right, I know what you're thinking. What is going on here? Mr. Wagner's absent today. I thought we don't have to do anything. False. You do have to do some stuff. And I am visiting you from my home. I am not sick. It's my daughter that's sick. So we're still going to go through Charles' Law. I know. I can see the smiles on your faces. And it won't be too terrible. But with the beauty of technology, that's what we can do here. So let's go through some Charles' law. It says Charles' law states that as the temperature of a gas increases, the volume of that gas increases. So um, take a look at this picture here. It helps out. Let's just suppose we have gas in a confined situation. Whenever we increase the temperature of that gas in that confined situation, it's going to increase the volume of that gas. So we see right here that we've increased the temperature. Therefore, we have increased the volume of that gas because this temperature is hotter and this temperature is colder. It goes along with the kinetic theory that we talked about at the very beginning of this chapter. Remember, the molecules of all substances are in random motion. Whenever you add more energy to those molecules, they move faster. Whenever you take away energy, they move slower. In this case, we're adding more energy, so those molecules move faster. And if they move faster, they're going to take up more space. This is not rocket science. Anyway, there's an animation that goes along with Charles' Law. Let's pause the video right now and watch that animation. So pause. Okay, great. Hopefully that was good for you. And take a look at this. More Charles' Law. Um, this is probably one of the best real-life examples of Charles' Law is a BLEVE, a boiling liquid expanding vapor explosion. Um, Take a look at this propane tank. This propane tank is on fire. Propane tanks have an emergency valve to release pressure in case they start to burn like this so they don't explode. However, in this one, they plugged that emergency valve and they're heating it up quite a bit. So what do you think is going to happen to the volume of the gas inside here as it heats up? That's correct. The volume of gas is going to heat up until this thing explodes. Which reminds me of a story way back when I was a kid. My job at home was to actually burn the trash at our house. We didn't have trash pickup where we lived, so my job was to burn the trash. And I don't know why my parents trusted an 8-year-old with matches outside, but I burned the trash. And I think my brother did this on purpose. He was kind of a jerk sometimes. He put one of these like degree spray deodorant cans in there. Normally our recyclables go in a different area. And I didn't know about it, so I'm stirring the fire to make sure everything's burned. I'm stirring it with a rake, and it sounds like a gun went off right at my feet. What happened was this deodorant canister, of course, as it increased in temperature, it also increased in volume. And as it increased in volume, it exploded. That's a great example of Charles' law. Let's keep going. Here's some more real-life Charles' law. As the temperature increases, the volume increases. So for example, if you do the reverse, why would a balloon shrink in a freezer? Well, I've got a freezer behind me here in my basement, right over there. I should probably stick a balloon in there. Wouldn't that be awesome? But I've got it on video. Why don't we take a moment, pause the video, and then you can look at this liquid nitrogen in the balloon, and you'll see that as the temperature decreases, the volume of that balloon will decrease. So let's pause the video right now. Okay, hopefully you guys saw that. You watched the liquid nitrogen in the balloon. Remember, decreasing the temperature, decreasing the volume. That's Charles' law. Here's another good example of Charles' law. Maybe the TPMS, the tire pressure monitoring system in your car. If you're going to get a driver's license soon, or your permit or whatever, you got to know about this because this light will turn on in your car at some point during the winter, usually the coldest day in the winter. This happens in my truck. I get in my truck in the morning, very, very cold day, and I see this tire pressure monitoring system. I'm like, oh my goodness, the tire pressure must be low. But it's not. Once you get your car moving and once it creates a little bit of friction, the temperature of your tires increases, which is actually going to increase the volume in your tires. But when it's really cold, it decreases the volume of your tires, which is another great example like NASCAR. NASCAR, when they do their warm-up or their parade lap, those cars swerve back and forth, and as they swerve back and forth, they actually generate heat in their tires, and as they generate heat, they increase the volume of their tires. So they start off running the whole track with not quite enough pressure in their tires, but they know after they do 2 or 3 laps, they're going to generate a lot of heat, therefore there's going to be a lot more pressure in their tires. So that's why they do that swervy thing at the very beginning of a lap. Oh, here's a this is interesting. So far we've talked about increasing heat and therefore increasing volume. But what if we switch it around? What if we decrease volume very quickly? If we decrease volume very quickly, we're going to decrease the temperature very quickly. Take a look at this t-shirt gun that the San Antonio Spurs have. There's a certain volume of gas, usually CO2, in a cartridge that's in there, and what they're doing is they're decreasing the volume of that gas very quickly. They're shooting all that gas out, so there's a significantly lower volume. That means the temperature is also going to decrease. Here's another example. I have an air compressor like this at home, and I use it to fill up my tires and bike tires and things like that. And one of the things you're supposed to do after you're done using it is you're supposed to empty all the air out of the bottom of this. And there's a little valve at the bottom that you can use. And I always think it's fun to empty the air out very, very quickly. Because when you empty the air very, very quickly, we are decreasing the volume very quickly, therefore we're decreasing the temperature very quickly. And it actually forms a little bit of ice right around the nozzle where the air is coming out because of Charles' law. Decreasing the volume, you're decreasing the temperature. Here's another good example. This stuff, actually, let me get some of this stuff. I found some. So we've got a certain volume of, oh, there we go. I've got a certain volume of air, or whatever chemicals in here. And if I release the volume of this very, very quickly, it actually lowers the temperature of the entire system. So if I if I do that very quickly, it actually lowers the temperature. Now this stuff can be very, very dangerous because if it blows out extremely quickly and you release all the pressure all at once, it gets really cold. In fact, you can develop some frost on the outside of this canister. And people have hurt themselves by doing this. But you're actually decreasing the temperature, decreasing the volume very quickly, therefore you're decreasing the temperature. And you can actually feel this can. It gets colder whenever you do that. And then, oop, colder. Maybe we'll try that when we get back to class, or when I get back to class, because you can feel it in your hand. You do that, and it just gets colder in your hand. It's crazy. Okay, anyway, that's Charles' law. Let's keep going. Oh, this is fun. The fire piston. Here's the deal. We talked about decreasing volume very quickly. And in this case, this is, hold on. Okay, I had to think about it for a minute. But this is a little bit different than using the canned air. In the canned air, yes, we are reducing the volume of air very quickly. But when we talk about a fire piston, although we are decreasing the volume of air very quickly, we're increasing the pressure extremely quickly. And there's a perfect gas law, which this chapter doesn't cover, which makes this case a little bit more complicated. But if you decrease the volume of something very quickly, but you increase the pressure extremely quickly, well, that's actually going to increase the temperature. And a good example of that is the slam rod fire piston. And whoops, let's go back real quick. Here's a good example of a slam rod fire piston. Basically, what you're doing is you've got a certain amount of air down here. You're going to decrease the volume very, very quickly, but you're going to increase the pressure very quickly, and it actually causes something to catch on fire. Let's pause the video for just a second. Click on the link here for the slam rod fire piston. Watch that video, and then we'll get back together. Okay, time's up. Good. Hopefully you saw that, and it made you think a little bit. It's really kind of cool. That guy's got tons of awesome videos. Okay, there is a math part to Charles' law. I know. Here's the formula we need to use. Hey, this is a proportion. It seems that there have been a lot of proportions in this chapter. This is just another example of proportion. So, here's the question. If a 2-liter balloon at room temperature, and room temperature in this case is 293 degrees Kelvin, which is like 30 degrees Celsius or something like that, is placed in a refrigerator at 276 degrees Kelvin, which is 3 degrees away from 0 Celsius, so it would be 3 degrees Celsius. What is the volume of the balloon once it cools? In other words, you got a 2-liter balloon, you're sticking it in a fridge, what's its volume going to be after it's in the fridge? Of course, we know the volume's got to be smaller than 2 liters. So our answer here better be smaller than 2 liters. Okay, 2 liters divided by the initial temperature, in this case 293, equals question mark over 276. Well, let's put in some of that information. We did our division here on this side, and we come up with 0.0068 liters slash, oh, I have Celsius. I should have Kelvin there. I'm sorry. It should be Kelvin, not Celsius. Please forgive me. And then we're going to multiply that times the 276. Remember the Celsius, which should be Kelvin, are going to cancel out. And then we're going to come up with an answer like 1.87 liters. Remember, we said our answer has to be less than 2 liters. Our answer is less than 2 liters. So it makes sense. Once you put that balloon in the fridge, we can calculate how small it's going to be, or at least the amount of volume that's going to be in there. Anyway, I think there's a worksheet that's going to go along with this where you're going to have to practice some Boyle's Law questions, and you're going to have to practice some Charles' Law questions. Anyway, ask Miss James for that. She'll hook up with that, and I think that's what you got to do for the rest of class. Anyway, have a great day. I'll see you tomorrow.